Okay, so welcome to our afternoon computer vision track. I hope you noticed that there were some changes in the agenda. You can see it online. And please take your seats. So our first speaker is going to be Professor Yaniv Assaf from Brainvivo, who is going to talk about the evolution of the brain and implications to AI. Afterwards, we'll have the deep learning-based video inspection for graphics processors and the practical explainability and tuning in DNN talks, right? It's not like the written printed schedule because there were a few changes. I hope you managed to cope with them. So without further ado, I'll let Yaniv start his own talk. Please go ahead.
Thank you, Amitai. Good afternoon, everybody. So first, let me introduce myself. My name is Yaniv. I'm a professor of neuroscience here in the university at the Faculty of Life Sciences and at the Segol School of Neuroscience. But I'm also the CTO and co-founder of Brainvivo. And today I would like to tell you a bit about what we are doing there. But before we'll start, a few words about brain evolution and visual perception, because this is the basis, well, actually this is the basis of AI at the end. So the evolution of the brain, or the evolution of species upon Earth, has created this amazing perception machine. So our brain is able to perceive information from the surrounding, from all our senses, but mainly from the visual domain. The visual system is highly dominant and occupied a large portion of the human brain. So obviously it's extremely important to get the information from our eye and present it somehow to the brain to get the perception of what we see. The question of how and where in the brain this perception occurs is still the central research questions in neuroscience. There is no good answer for that. But from all we know so far, the pioneered work of Hubel and Wiesel, the discovery of receptive fields in the visual cortex, paved the path to an hypothetical mechanism of how the brain gets the information and create a receptive map of what the eyes see. Recent evolutionary studies have tried to look at how evolution created this receptive field. And in this specific study, these researchers look at the receptive field of different species, and indeed they found that the receptive field, at least for orientation dominance in the visual cortex, have evolved through the last 60 or 70 million years. However, they did found that certain species, for example, rodents, a rat, a mouse, they don't process visual information with receptive fields. The neurons that are sensitive for orientation or for moving object are like a salt and pepper pattern in the brain. So could it be that receptive field as itself, as we see in the human brain, is not responsible for our visual capabilities, because rodent can still perform object recognition and other visual tasks. So regardless to the answer, are receptive field necessary for a visual perception, it has become the neural architecture, the neural network, and the neural networks within receptive field become the basis of another field of AI, of the evolution of artificial intelligence. So if we'll start to build it as an evolutional tree, to look at the AI as an evolutional tree, and we look at the AI common ancestor, that will be a neural network algorithm. From that, it has evolved through different approaches and different algorithms in order to do machine learning, and then deep learning, and other applications of that. But it becomes apparent to all of us that there is like a glass ceiling to what we can do with this kind of application. There are areas where even deep learning, no matter how many examples you'll give them in the training set, will fail at the end. And there is an idea that is coming around in the neuroscientific and also in the computer science communities that at the end we want to do something that will be brain-inspired AI, because we know that our brain has capabilities that are still far from being achieved by any artificial intelligence platform. And this is what we do in Brainvivo. So Brainvivo decided to take an experimental platform, which I will tell you a bit in a minute, and create a real brain-inspired machine that can solve AI challenges with human brain intelligence, intuition, and more importantly, judgment. Because if we think of a brain as a cognitive system, the main ability of our brain is to create a judgment, to judge something. And that's something that a computer cannot do. But what will be this brain-inspired machine? So let's move on about 10 or something years from now, when brain-inspired AI will exist. What will be the application of that? So let's look at that example, where judgments comes into AI. For example, let's look at this poor guy that needs to buy a present for the birthday of his wife. And he say, if I only could get into her brain and see what she wants and see what she expects to get. With an application, he can download her brain, her digital brain that was scanned, and go to Amazon or to some digital store, and then just scan the different things in the store and decide what she would want, and that would be exactly what her brain wants to get. And you can think of other examples. For example, job interview, a thing that all of us experience, which is a very difficult situation. Some people are shy, some people are how to do the interview. But you can think that you can send your brain to an artificial interview, and where the brains of you and the HR agent that sits in front of you interact by themselves, and then they can judge, do we want to hire that person or not? So adding judgment into artificial intelligence will obviously have an influence of how this field is going to be 10 years from now. But how can we do it? So with this evolution tree of AI, where can we add the brain aspect of it? And let's go back to the common ancestor of AI. AI is built on neuroscience. It's built on models of neural learning. We all know the Hebbian learning rules, the McLaughlin neuron, Turing test. All of them are built of how neurons can interact with one another to achieve learning. If we take Heb rule, which is the rule of wire together, fire together, wire together, or strengthening of a neuron based on learning, or weakening based of negative learning, it is all based on a very simple mechanism in the brain, which is synaptic activity. This is how neurons work. Neurons work by strengthening or weakening their connections with other neurons. And through that evidence, which is still valid today, we have these models of neural learning, which are the basis for all the things that we do in AI. So that brings us to the Synapse Doctrine of AI. AI is built on the Synapse Doctrine, that the synapse is responsible to everything in the brain. We know from Donald Hebb that synaptic plasticity is the mechanism of learning. We know from Hubel and Wiesel and Hartline that receptive fields leads to perception. This is the theory behind it. We know that we don't know, but it is assumed that brain connectivity is a simple graph. In any network that you are using in deep learning, everything is connected to everything at the end. So this is a simple or a complete graph at the end. This is neuroscience of 1950. Believe it or not, neuroscience has advanced since then. And today, almost at 2020, we can say a lot of other things about how the brain processes things that might push the ground behind this theory. So we know, especially from neuroimaging, so neuroimaging is one of the major tools that we have today to inspect the human brain in vivo, which is a great advancement. We know from microstructural MRI that learning happens beyond the synapse. Synapse is not the sole mechanism that is behind learning. Through slow event-related fMRI, functional MRI, we know that perception is much more complex than the receptive fields that we are aware of today, in a manner that we will probably cannot understand. From a new field that is called MRI connectomics, we can understand how brain connectivity regulates learning and puts rules on how the brain perceives information. So with these new rules, we can define maybe a new background in order to create a brain-inspired machine. So let's give you like a scientific taste. Again, I want to show you what Brainvivo does, but it is based on a lot of scientific facts that we have gathered in the last year. So AI, neural network and synaptic activity, this is the basis. But in neuroimaging, we have learned that learning and plasticity goes beyond the synapse. So this is a computer game, The Need for Speed. I'm sure that many of you have played it. Who've played The Need for Speed? Yeah, put your hands up. It's good for your brain. So the Need for Speed is a spatial navigation task. This is a spatial learning task. You need to remember the track that you've driven in the car in order to complete it. By performing MRI before and after this task, we were able to see microstructural changes within 2 hours of playing that game. There is no neuronal mechanism, not synaptic, nor any other neural mechanism that can account for that kind of change within 90 minutes of playing a computer game. There must be additional mechanism. Through histology in rodents, we were able to see, so you see the green cell here. This is for a rodent that didn't do any learning at all, and this is for a rodent that performed a rodent version of the Need for Speed. But you can see that there is a major change in the shape of these green cells and the size of them. These green cells are not neurons. They are called glial cells, astrocytes. Astrocytes because they look like a star. And we do know now from the last 10 years, 10 or 15 years of working on astrocytes, that they have an active role in learning. Some may think that they are the first one to learn, and then they tell the synapses what to do. And obviously, it's a mechanism that we oversaw. Oversaw in neuroscience, for sure, and then oversaw in artificial intelligence. So the first thing that we learned from science is that glial cells, another type of cell in the brain, which outnumber the number of neurons by a factor, plays a central role in learning. Additional evidence. So in neural networks appears to be a fully connected network as we do in deep learning or in neural networks. But we do know from brain connectivity experiment that the brain is if we put it on a graph representation, behaves like a small world network. So for that we use what is called MRI connectomics, creating with MRI the wiring diagram, the blue diagram, the wiring diagram, the blueprint of brain connections. And from break, it's hard to see with the lightning, but you can create a connectivity matrix. Which area, which neurons, clusters, we call it like that, which areas in the brain wire together or communicate. And for sure, this is not a simple graph. This is not, for sure, a fully connected graph at the end. We were able to get rules about how the brain connects through an evolutionary study together with my colleague Yuval from the School of Zoology. We were fortunate enough to get a brain sample of more than 100 different mammalian species. And from that, we were able to see that there are laws of connectivity that are beyond evolution, that can be found within species, between the heterogenic variability between us. We have 2 hemispheres. There are connections between the hemispheres. And this is the mechanism how the brain regulates learning, how it regulates plasticity. Because if you learn something, and there is addition to your brain, you need to lose something. It's a closed box. At the end, it needs to minimize its energy. So there is a mechanism that through the connection between the hemisphere, when you learn something, the connection between the hemispheres need to change. This is what we saw in the graph without getting into details. But at the end, we were able to plot all the brains in our samples. There were more than I think, 250 different samples, and including humans, we got to about 1,000. At the end, you can build a graph that shows you what is the relation between the cost efficiency in the brain and the cost, so the efficiency versus the cost. And you can see that there is a peak for this graph. This peak is the small world zone, which means that the brain behaves as a highly efficient network. And there are regulation laws, and we need to use them in order to create a brain machine. So the brain connectome, if we can measure it, and we can, regulates plasticity and learning by cost efficiency minimization of the conservation. And the last scientific evidence I want to show you is how perception, what we think in AI, goes through receptive fields. We know now that perception, our ability to understand what we see, what we hear, what we sense, is processed globally in the brain. So this is example for the brain representation through slow event-related fMRI of specific images. So this is, there are 3 images here. And in a minute, a movie will start, will be a slow version of the variation in activity in the brain of a real subject, that is me, that saw these images. And you will see, so it's a very slow version, you will see that after a few seconds, the visual cortex start to get a lot of information, which has to be, it's a visual input, but then you see that a lot of things happens in the brain. So let's start, the movie starts. So this is just the movie, the images came in, and you can see that activities start to be built in the visual cortex, but a lot of things happen on other areas of the brain, which means that when I see an image, it's not that just the receptive fields in my visual cortex that are active, a lot of other areas in my brain are active, trying to understand what I'm seeing. And we need to take that as information in order to create a more accurate machine of the brain. Let's take another picture. So here, what we see, a man climbing on a rock. All right. So, and this would be the answer to the question, what do you see? But another question you may ask, and our brain does this automatically, what do you think of this image? All right. So we took 3 people and asked them this question. All of them said, it's a person climbing on a rock. Of course, this is what's in the image. But what do you think of that? So one of them said, it's exciting. One of them said, it's scary. One of them said, it's boring. And when you look at their slow event-related response, you can see that it is quite different. So it's the same visual input, the same visual stimuli that came into their eyes. It's the same visual receptive field, but there is a different perception for each of these people. And we want to get this perception. This perception is judgment. We want this judgment. We want to model it. So brain response to stimuli evokes whole brain connectivity regulated and time-locked activity that leads to eventual perception. It's not a completely different concept from receptive field, you just put it on a different scale. So can we use these concepts in order to build an AI machine or brain-inspired AI machine? So for that, we need an MRI, we need a stimuli that together put them together somehow, in a minute I will tell you how, and produce from both of them a digital brain, an avatar for each of our brain that will be able to process information as similar as it can to the real brain that is behind it. And it won't be a similar machine for each one of us. Each one of us is different, has different perception, then each one of us that will be scanned will have a different machine on the other side. So what is the brain model? The brain model is to scan a subject, or subjects, or many subjects, as much as we want. MRI is not as expensive today as we think it is. And let them see a set of images. And for each one of these images, we get a brain response. And that brain response is not a single number. It is spreads all over the brain. In our analysis, we started with 1,000 regions in the brain. So it's like 1,000 independent dimensions that models the information that is given. And as the model it builds, it takes, and I don't have time to go into details, but it takes global image features. It has to be global. In a minute you'll understand why. And relates how each brain region responds to each feature, to each global feature. So we can model, like we have 100 linear models of how the brain responds to each of the features in the images. So it's a very complicated image, a very complicated model. But once we have the model, we can go the other way around to give the digital brain an image and create what would be the brain response of it without a person seeing that image on the other side. Just to make sure that it's not nonsense at all, we did a validation. After giving the digital brain to see that image, we gave the real brain to see that image, and you can see that there is very high correlation between the information. That means that the model works at the end. So we can recreate, we can re-simulate what would have been the activity of that specific brain. of that specific brain, even if he didn't see the image at all. Once we have this brain model, we can go one step forward and give it test images, as we do in MI. So we give him a test of images which we know what they are. So this is like unpleasant image, right? Create the brain response to the simulated brain response to that image, and then compare it to a training set. So we have training set of brains that we know what is the brain representation of categories: pleasant, unpleasant, happy, unhappy, or whatever images you want to see. And in the end, we can make a decision. We can make judgment. Is that image that nobody has seen before, only the digital brain, is, for example, objectionable or non-objectionable? For example, we'll see here in a moment a few more examples. I will show you 3 examples about how this digital brain can classify information, how this digital brain can do content moderation, and how we can deal with fake media. So for classification, we took a very naive test, but it can be solved with deep learning, for sure. Classification can be solved. We took 7 categories: faces, three items of food: eggs Benedict, steaks, waffles, and 3 scenery items: beaches, deserts, forests. And you can see that you can also do some hierarchical clustering of that. So you have the faces, this is one category, you have foods, and you have landscapes. And you can see what is the brain response for all of them. But just look at it. In the training set, just because it's a brain at the end, we scan a brain. The brain comes with a lot of data inside it. It comes with your data of your lifetime. We don't need as many images as deep learning needs. So in the training set, only 60 images. The simulated brain saw only 60 images. And we compared the brain model with other models of machine learning. This is the brain response, the simulated brain response of the faces, the 3 different kinds of foods, and the 3 different kinds of landscape. So this is 1,000 brain regions on the y-axis, and this is the categories on the x-axis. And you can see that within a category, for example, the 3 different kinds of foods have very similar brain response, but it's quite different from the other categories. And when you see and you look at the brain representation, you can see the differences between them. This is the confusion matrix of the simulated judgment, the simulated brain judgment of what these images are. And you can see that it was very accurate, almost 80-something% accurate in deciding what's in the image, what is the category of the classification of the image. Again, only 60 images in the learning, in the training set. And when he did a mistake, they were always within the category. So when he said that something is not a waffle, he said it's a steak, but it was always in a food. And that gives you an idea how the brain works. The brain categorizes information. First it's a food, then it's something, then it's subcategorized. Right? So in terms of receptive fields, this tells you what is the hierarchy of perception receptive fields in the brain. So just to compare the different models, so the brain model got 80-something%. The other, probably naive models, failed to do the classification on 60 images training set. Another example is in content moderation. So content moderation obviously is a big issue today. No need to say it, that governments want to regularize it, to do regularization of that. Facebook, YouTube are investing a lot of money in order that harmful content will not go into the media. For example, YouTube just said that between July and September 18, they removed 7.8 million videos from the channel, and Facebook 15.4 million items were removed. So obviously that's a main issue. And just at the bottom, it's written that Facebook says that 99.5% of the material was taken down by a detection technology. So you would think that AI will be able to handle it, and the answer is that it can't. And the detection technology is 100,000 people that are sitting in India, in the Philippines, in Colombia, and just tagging the images. So this is the AI behind content moderation. And there are also issues of fake accounts and other harmful information of child abuse that needs to be removed from the media. So what we did, we took 3 categories of faces or body. bodies. So happy faces or happy pictures, a violent picture, these are blurred just that you won't see the information behind it, and nudity. And we asked our brain model to classify it, if it can automatically detect that. And again, the training set was very lean, 60 images only. And you can see the brain response. So since it's bodies and faces, it is very similar. It's not a face and steak, all right? So the brain response will be similar, but there are some difference between them. So you can see that the response for a happy face is quite different, especially in this area from a violent, and nudity is much more expressed in temporal areas where the amygdala is, if you know what it is. In terms of achievement, so the brain model was able to separate at 80-something percent accuracy the different categories, where the other models failed at this level of small training set. Can you tell, the last example, can you tell which of these faces is fake and which of these faces is real? I can tell you that if you look at each of these images closely for a minute or so, you will be able to tell, because you can find small details that are unreasonable. But at first glance, it's very difficult to say. Can you say now who is the fake and who is the real? Is the blue the fake, or the red, or orange the real, or otherwise? So the red is fake, the blue is real. And what we asked our model, so we took 120 images per category. The fake ones were taken by the GAN-generated face algorithm, and the real faces were taken out of Instagram. And we use again our model and the naive other model. What you can see here is the brain response. To real and fake faces, and you can see that it is dramatically different. So our brains can detect. It might take a while for us as humans to do so, but the digital brain can do it quite rapid. So the brain response is quite different between real and fake images. And when you compare the models, so this is the brain model, 99.3% accuracy. It was able to almost separate fake faces from real faces almost completely. The other model, the convolutional neural network, did also nicely, but didn't reach that level of 100%. And when you have fake information coming in, you want to be totally sure that it is gone from the web. So to summarize, our brain evolved through millions of years to be an efficient learning and perception machine with the mechanisms that is far beyond our understanding, and maybe we will not be able to understand it at the end. But it doesn't mean that we can't image it and model it. So through MRI, through advanced MRI, we are able now to create a model that links stimuli to brain response. And through that, we can use this brain avatar, this digital brain, in order to perform AI tasks, judgment tasks. It appears so from the examples I showed you that brain-inspired learning machine outperforms conventional machine learning algorithm, especially when the task has to be judgment. And especially when it has to be individual judgments, because a picture that might be unpleasant to my eyes could be pleasant to another eyes, and we want this heterogeneity to be modeled at the end. And I think, and this is the way we are going in Brainvivo, that future NI must adopt real brain functional architecture. There's a way to go, but I think we need to put the seeds now in order to see this technology coming up a few years from now. So we need to adapt AI to meet the expected users, the future users that we want AI to have. And just to note, in terms of evolution, so this is the evolution tree of all species on Earth, or all organisms on Earth. Just to note, neural network as an algorithm is like a worm in terms of its complexity. So it's here in the evolution tree. Deep learning is a bit more advanced. It has some layers of information processing that happens in fish, for example, in the evolution tree. We are here. Our brain can do much more than that. So it's high time that we'll shift our algorithm in AI to meet what mammalian brain or human brains are doing and get all the goodies that our brain can do. So remember, there is AI in brain, for sure. And I want to thank you and thank my colleagues in the university and my colleagues in Brainvivo that are working with me, and thank you for your attention.
We have about a minute for a quick question. Yeah?
I can give many details. The model itself, the idea, let's speak about the concept. The idea that you can't look for example, if you want to do face detection. In face detection, you look for eyes, you look for nose. You can't do that in that model. This model has to work globally, because when you put an input image, I don't know what's inside. So you have to model it globally. So there are global features. I can give you an example for one. Entropy. Entropy is a global feature of the brain. So you can model what is the response of each of the 1,000 brain areas to entropy of an image. And when a new image comes with different kind of entropy, you'll get its response. Eventually, you will, through a list of such global features, you will be able to recreate what is the real brain activity.